Right now we're going to have a talk titled as Dynamic Huff's Gravity Model with Covariance for Site Visitations Predictions. And we have our wonderful guest speaker, Mr. Winston Lee. So without any further ado, I will go over his bio. Winston is the founder of Arima, a Canadian-based startup working on synthetic customer data. Our flagship product, the Synthetic Society, is a privacy by design individual level database that mirrors the real society. Built using trusted sources like census, market research, mobility, and purchases patterns, it contains more than 50,000 attributes for hundreds of millions of individuals across Canada, US, and enables advanced modeling at the most granular level. Aside from Arima, Winston is an avid researcher in data mining, where he publishes in outlier detection and synthetic data generation. Winston is the co-creator of PyOD, one of the most widely used open source Python toolbox for data mining. So without any further ado, help me by giving him a warm round of applause.
All right, thank you everybody. I know it's the last session before lunch, so I'll go real quick so that everybody can get out of here and eat lunch. All right, the dynamic Huff model with covariates. Let's start with chatting about what the Huff model is. The Huff model is a spatial analysis model used in predicting the probability of somebody visiting a specific location. So somebody could be a consumer, could be a visitor, could be anybody visiting a store, a location, you know, a national park, some scenery, an office building, whatever it is. And the way that Huff model makes its prediction is based on factors like distance, attractiveness, as well as attractiveness of other alternatives. This is a really old model. It's been proposed in the 60s, 1963 to be exact. And since then, it's gotten some pretty good traction among people in marketing, in urban planning, in economics, and in fields where we worry about physical locations and where people go in the physical world. In the original paper, this is how the Huff model is proposed. And of course, we'll go through that first, and then I'll talk about what are some of the new ideas we've added to the Huff model. So if you look at the equation on the screen, we have the probability Pij, which stands for the probability of someone, a customer I, visiting a particular location J. This is ultimately what we want to know. That probability is dependent really on two things. One, the attractiveness parameter, which is identified as A here. That's a measure of how attractive a particular location is, or that particular location is. Now, attractive is really hard to define. So in a lot of the work that people have done in the past, they've simply used the size of the location as a proxy for attractiveness. So the larger the mall is, or the larger the store is, the more attractive it is. It's not exactly attractiveness, but size is easier to measure, so that's why people use it. And then the other parameter that it depends on is D, which is the straight line distance from where you live, where the customer lives, to where the store is. So the further away you are, the less likely you're going to go there. And lastly, you've got these parameters alpha and beta, which are the attractiveness and distance decay parameters. The logic for that is if something is, let's say, really, really far from you, your likelihoodness of going to that location will drop exponentially. So if something is a 10-minute walk from you, maybe you'll go there. If something is, 10 times as far as that, you're not just, only 10% likely to visit that location. You're probably not going to go there at all. So there is some exponential decay when locations are very, very far. And same thing with attractiveness. If something is really, really not attractive, you're probably just not going to consider that place at all. So therefore, there is that decay parameter. And then finally, N being the number of stores. So really, you're looking at the overall attractiveness, overall how overall attractiveness of the location versus, divided by how many locations there are in total. Let's take a look at what this looks like when you plot it out on the map. So here you can see we've got 3 Walmart locations. This is somewhere in Washington, in the States. You've got 3 Walmart locations, and then based on that, you see a contour plot of circles. So within this first location, for example, you can see this location on the top right. You see a little red circle. So everybody within that is highly likely to visit that location. So that's 90% or higher. And then there's a ring around it. That's your 80%, and then another ring further to that, and so on. And then if you're out, let's say over here, close to where the legend is, you can see the probability of you going to any of the locations is pretty low. It's only around 40%. So that's the Huff model as it's been proposed back in 1960s. And there are a couple of problems. I mean, ever since then, that's basically the version of the model. And there's a couple of problems with that model. There are 3 internally. There are, when we were looking at the Huff model, internally, there are 3 problems that we found. And the first being that the model is site-centric, not consumer-centric. So the attractiveness is really depends on the property of the location. So, the larger the store is, the more attractive it is. But in reality, people may have different views on what attractiveness means. So person A may find a certain type of store attractive. Person B may find a different type of store attractive. So that's not being factored in the model. Second, back in 1963, people had to use straight line distances. So if I'm 5 kilometers away, then my distance is 5. If I'm 10 kilometers away, my distance is 10. Now the challenge with that is it doesn't factor in ease of travel. So maybe I'm further away, but I'm right next to the highway, and I can get onto the highway easily, and I can get there faster. Versus you might be closer, but it's physically harder for you to get there because you have to take the ferry or take a bridge or something like that. So that's also not being considered. And of course, this can be easily done today via the use of mobility data, as we'll talk about in a little bit. But back in 1960s, there were no mobility data. There was no cell phone. So that was obviously very different. And lastly, change in time and seasonality is not being captured. So if a particular location is attractive, then it's always attractive, and it'll remain attractive for every day of the year. So we've been, over the past 6 or 7 months, we've been experimenting with something called the dynamic Huff model with covariates, and we had some success with it. And here I am sharing what we've done with all of you. So first of all, dynamic really means it changes with time. So time is a factor in the model, and time is being factored in. And covariates really means features. So we're adding features into the model so that, one, we're factoring both properties of the site as well as properties of the visitor, and we're calculating which of these factors or which of these covariates help explain visitation a little more. So here's what we've done. Attractiveness, if you recall from the previous discussion, attractiveness was really just a size of the location, but now we're turning that into a function. So attractiveness is a function of 2 things: of site properties, so things like the size of the mall, its pricing, visitor demographics, maybe the number of washrooms, maybe how many years since the last renovation, all things that are important for the business to understand. As well as consumer preference. So as a consumer, what do you like? Does this location, does it have your favorite stores? What's your buyer psychographics? Are you into things like organic food, or are you into things like certain ethnic products, and whether that particular store matches your buyer psychographics? There are obviously many more factors that you can include within the model, but the point here is that attractiveness itself is no longer a single dimension measurement, but rather a whole function, a whole equation of many factors. Here you can see what we've done is we've turned A as the attractiveness parameter as a function of many factors, each of which has its own weights. This is essentially a linear regression model, a regression model within the A parameter. And depending on what you believe, you can use a linear model, you can use a log linear model, you can use a log model. Remember, in the original Huff model, because attractiveness is exponentiated, so you have a little decay parameter, one may believe that they might want to use a log model or a log linear or log model. Internally, we've just used the linear model and it worked very well. So that's that. Distance, same thing. Back then, it was a straight line distance. Now we're expressing distance as the amount of time required to travel from time A to time B. And again, I'll discuss how that's being calculated in a second. Lastly, distance decay parameter, that stays the same. And finally, A and D both depend on a specific time period. So you can run this model on a weekly basis, on a monthly basis, on a quarterly basis, on an annual basis, whatever makes sense for your business. But the point is, some of these parameters and some of these covariates should change over time because of seasonality. All right, I'll run a quick example through what the model looks like just to show you an example, and then we'll take a look at how the model is being constructed. So let's take Jane as our hypothetical customer. Let's say Jane lives around Hyde Park, and when it comes to grocery shopping, she's got three options. She can go to Costco, which is 30 minutes away. She can go to No Frills, which is 15 minutes away, or she can go to her local convenience store, and that's only 3 minutes away. Some of her characteristics include she has access to a car, so she can drive very far. Her preference for distance is not as high. She likes to have all her shopping done in one place, so she really likes bigger stores versus smaller ones, bigger groceries. She's new to Canada. She prefers shopping. She prefers shopping with other newcomers. So the demographics composition of the store is very important. She likes to go to places with fewer shoppers, so quieter places. And lastly, she's influenced by ads, so the number of times she's been exposed to some advertising is important. Here's what a finished model may look like. And obviously, we'll have to discuss how these parameters are being calculated, but let's assume that these coefficients are there. Here you can see we've got our four factors. Square footage, remember she prefers to have all her shopping done at one place, so the larger the store is, a greater preference will be given to that. The percentage of similar shoppers, that's also very important. That has a positive coefficient, so if it's a store that's generally liked by other newcomers, she'll like that as well. Daily traffic, that has a negative coefficient, so if the store is busier, she doesn't like that. And finally, the number of ad exposures she received, so the number of times she's seen an ad. If that store has advertised to her more, then she would like to come there more. Now, I'm only using 4 factors here. In reality, some of the models we built have 50 or 60 different parameters, but this is just a toy example to show you how the model works. Once these parameters are calculated, we can now take the 3 stores we have and we can plug in the numbers we know. So square footage, it's a simple matter of looking up these stores and figuring out how big they are, what are the square footages. Percent of similar shoppers, so Costco, everybody goes there. It's not particularly designed for newcomers or not designed for anybody, so only 10% of the shoppers are similar to her. No Frills, 50%, and convenience store because it's in her area, so a lot of other people who are like her live in the same area, so that's a 70%. Same thing, daily visitors, we're going to get the daily visitors of each of these stores, so we have these numbers. And finally, the number of times an ad has been served to her. Again, we know these numbers, so we can plug that in. Then it's a matter of calculating the attractiveness, which is the dot product of the two vectors, calculating the inverse distances, and finally multiplying them together. And again, if you follow the Huff model equation, which I had on the previous screen, you could calculate the probabilities of Jane going to one of the 3 stores. So here we work out the math, and it says that she'll go to a Costco with 52% chance, a No Frills with 34% chance, and convenience store with a 14% chance. Again, if you make the assumption that she visits some grocery stores every week, then multiplying that number by 54 gives you the average number of expected visits for a year. So in a year, on average, she'll go to Costco about 27 times, No Frill about 18 times, and her convenience store only about 8 times. All right, now we've looked at the model and how the model works. Let's look at some of the ingredients that go into a model like this. So to train a model like this, we need 2 things essentially. One, we need to figure out which covariants are meaningful. So what factors do you want to include? What's important for the business? As well as some way to optimize and figure out the unknown coefficients. To do so, we need 3 pieces of information, 3 different data sets we'll talk about. One, you need some point of interest data. So you need to know where the stores are. You need to know how big they are. You need to know where they're physically located. You need to know what type of a store that is. Is it a grocery store? Is it a, is it a bank? Is it a whatnot? 2, you need movement data. So you need to know where people move throughout the day, because as you see from the analysis, a lot of the calculation depends on knowing who you are, how far does it take from you to get to place A to place B? What's the likelihood of you visiting there, and so on and so forth. And finally, number 3, we need visitor behavior data. So we need to know factors about your customers like Jane. We need to know their things like their price sensitivity, their, are they new to the country, things like that to help fine tune the model. So I'll share some of the data sources we use when we built the Huff model. The first data set we use is called Overture Maps. It's an open source data set for people who build maps or geospatial analysis. It's open source. It's built, I believe, by Microsoft and Apple and Amazon, some of the bigger guys, and designed to help to create an open source version of Google Map, essentially. Within that, there's about 440 gigs of POI data with stores, locations, administrative boundaries, roads, a lot of things in there. So you could very easily tap into a data source like this, where you can find location of stores as well as how big they are. So not only do you get the location, but you very often also get the polygons of the store. So this is one of the most useful and open source data sets you can get, in my opinion, if you work in this area. The second data set you'll get is mobility data, and this is also something that we've been working with for a very long time. Essentially, mobility data tracks people's physical location from your phones. So if you're carrying a phone, chances are you are sharing your physical location with somebody. The data set is really simple. You get a timestamp, so you know where it is. You know when that is. You know who it is, so you get an advertiser ID, as well as you get a geometry, so basically a lat-long pair. Everybody gets pinged a couple hundred times a day, so there's lots of data, and basically you know where people are throughout the day. I have a little picture of what the data looks like in its data format, in its CSV format, as well as what it looks like when you actually plot it out on a map. So if you plot it on a map, it looks like a heat map. If you join it by time, then you'll have a path on that map of where that person is. And there's lots of interesting applications with mobility data alone. You can calculate who goes to where, how long do people stay in certain locations. Like if you're a store, you can calculate how long people go there. Do they stay there for 10 minutes, for 30 minutes, for an hour, and so on. And you can also actually target a lot of these individuals. These device IDs or these advertiser IDs, although they're fully anonymized, they could be actually targeted. So you could say, I'm interested in figuring out who visited my store, and then show them an ad afterwards, or show them an ad, let's say next week, same time, hoping that they'll come back to your stores. And the last piece of data that we use is something that we offer, and this is what we call the synthetic society data set. And before we get into that, I'll talk a little bit about what synthetic data is. Synthetic data are data sets that are algorithmically generated. They are not the same as your real or original data sets, but they do preserve nice statistical properties of your original source data. So think of it as kind of a carbon copy of your original data set, except it only contains all of the useful statistical information. Like other generative models, synthetic data creates data. It's a process of creating data from data. So the way I sort of like to think of it is, if you've got lots of text, you train a model on that and you create more text out of that. That's your GPT model. If you have images and you train a model and you create more images out of that, well, that's your Midjourney. And if you have some data, you train a model and you create more data, well, that's what we do. Synthetic data solves many problems. The biggest ones are privacy. Privacy being when you're dealing with consumer data, privacy is obviously a very big thing. A lot of times people simply anonymize data sets, but sometimes even anonymization isn't good enough. Even if you remove people's identifications, like their names or emails, there are still sometimes re-identification risks. So that's a nice property of synthetic data, because synthetic data only preserves the statistical properties, but your data is nonetheless different than your original. So you will not be able to see two records that are identical, and hence you won't be able to trace back to anybody, but all the nice statistical properties are preserved. And synthetic data is also a good way to create data fusions. Sometimes you have multiple data sets. There isn't necessarily a way for you to join them together. There isn't a very good way for you to match. So there is no name, no email, none of that, nothing for you to be able to match. So a better way to do is to actually just train models on that. The model will be able to learn properties from both data sets and then generate more data sets that contain properties of both data sets. So one analogy I like to use is you've got two pictures. You'd like to see what happens when the two pictures are merged. Well, you can train a model and generate a synthetic image that contains nice properties of both pictures, and yet that image that's being generated doesn't actually exist anywhere. But it's still useful. So here, a little bit about us. We have a data product called the Synthetic Society. It's essentially a digital twin of the real society. Basically, we take a lot of source data, we train models on that, and we use that to generate synthetic individuals. These synthetic individuals are generated to, in the best way possible, mimic real people that live on the planet. We used to be US and Canada only. Now we're global, so we've got 53 countries with 4 billion people, 4 billion synthetic people. Everybody has 50,000 attributes, so there's a lot of things we know, or at least a lot of things we know synthetically about people who live in Canada, in the US, live on this planet. A lot of that includes, social sort of demographics, socioeconomics, behavioral, personal finance, healthcare, you name it. So there's lots of things in there. And then our individuals are aligned to geographies. So it's particularly useful for geospatial type of analysis. All right, just a couple of slides left. I'll talk about how we train and build a model, build the Huff model, and then that's essentially it. So the steps of developing a model. it's really straightforward. It's a six-step process. First of all, you identify a point of interest. So, if you're making a prediction about how many people are coming to Loblaws, well, Loblaws, that's your point of interest. You also have to identify its competitors, but that's fairly easy to do. Most businesses would know what their competitors are. Even if you don't, in a source like Overture Data, it contains all of the locations within that category, so you could simply pull up other stores. You want to identify a list of visitors using mobility data. So basically, you look at your stores and you see which devices visit that location. You can do that very easily through a data extraction. And once you have the list of visitors, you can empirically calculate what's the probability of a particular visitor visiting your store versus other stores, just by simply counting how many times they've been in your stores, how many times they visited the competitors. Like almost every model, you have to empirically calculate the probability first and then train your model. So mobility data is what we use to empirically calculate the probability of visitation. You come up with a list of location attributes and visitor attributes. I had a little typo up there, but I'm sure you know what that means. So go through your stores, go through the list of data you have, figure out what patterns, what features are important for your business that you want to understand. And you also want to calculate the travel time between location I and location J. So that you can get very easily through an application like Google Maps, which is mobility data based as well. Or if you prefer, you can also use straight line distances to make it simple. So again, if you go back to the model, you'll see that these are some of the ingredients we have. The attractiveness, we have all the covariates. So it's basically nothing more than a regression model of trying to figure out what the coefficients are. As well, you'll also have to calculate your beta, which is your location decay function. But it's nothing more than an optimization problem where you have some training data, you have some unknown parameters, you have a loss function, which we just use the cross entropy because it's a probability, and your job is to figure out what the coefficients are. So it's a really straightforward model that helps you, where you can use to calculate these unknown coefficients, which is really what you're looking for. And once you have these coefficients, obviously now for new customers, you can use that as a way to predict what their probability of visiting are. And last slide, I'll just quickly run through some use cases. Why is this useful, or how could a company use this? Well, there's a couple things that we've done in the past. Scoring customers is something that we've done many times. A company may have a list of customers. They'd like to know which one may come back next month, next quarter, next year, and which ones will likely churn. And for the customers that may churn, they may want to send them an offer, do something with these customers. Identify factors that drive visits and support site selection. So why are certain stores popular? Why are certain stores not as popular? And what factors drive people to come there? And if I were to open up new stores, where do I pick which locations are better? And same thing, you can do that for your own locations, and you can do that for your competitors' locations. So if you recall, none of this data set depends on anything that you would need from your competitors. So in theory, you can run the same model for your competitors' stores as well. And lastly, measuring ad efficacy is also something that a lot of our customers do. So if I advertise in a certain area, does that improve the probability of customers visiting my location? And if so, does that justify my ad dollars? So those are some, I'm sure there are lots more applications, but those are some of the things that we've done in the past. And that's it. So
Hi, Winston. So I guess my question is, like in the example you showed for Jane, oh yeah, that's a good idea.
yeah.
Are are these like the actual like variables that Arima uses? And if so, like how do you guys choose them? And I guess another question is, does it matter if like these variables are like dependent on each other? Like I could see like square footage being, and like daily visitors, for example, like being dependent. Like, does that matter, or do you guys like try to like extract the principal components and then like optimize from that? I don't know.
So are these the factors we use? These are some of the factors, but generally a lot more. Usually you're not going to get a good model with just 4 coefficients or 4 parameters. So we tend to include a much larger list than what we have here. But this is obviously just for illustration purposes. So that's number one. Some of the models we ran, we found that if you wanted a good fit, like if you wanted a pretty accurate prediction, you're probably looking at somewhere between 50 to 70 features at least. Just because it's inherently fairly noisy. Like people's movements are hard to predict in general. So that's one. Number two, multi-collinear. How do we pick these coefficients and what happens with correlation? In most of our cases, the business had a pretty good understanding of well, I shouldn't say they had a pretty good understanding, but there were very specific reasons why they want certain variables to be included. So for example, let's say, let's say number of ad exposures as an example. There's a very specific reason why people wanted that. They want to know, should I be advertising in this area more or less, and so on. So there are definitely variables where the business requested that to be included. You can also go through the standard variable selection process, like because you have a loss function, you can run different variables, see which ones to include and which ones not to include, and whether that impacts your accuracy. So you can also select variables that way. It's really no different. It may look somewhat unusual, but it's really a nonlinear regression. So people could use the same ways as how you deal with a nonlinear regression problem. Yeah.
Okay, thank you.
Thank you for the talk. Thematically similar question is, like, one of the use cases that you showed was trying to understand the effect of these different factors on behavior. Is there any risk with people using that and taking a causal interpretation of these coefficients that you're estimating? Like, you're optimizing everything jointly. Is there kind of endogeneity problems also with regard to maybe distance with regards to certain types of things that affect people's distance? And just optimizing it all jointly, do you also consider other methods for people wanting to use a causal inference type use out of this?
You can. We haven't tried that. And yes, internally, we did run into a lot of, I wouldn't say a lot, but sometimes it does happen where this thing doesn't converge at all. So yes, the nonlinear nature plus how variables are being selected, you could run into problems, yeah. We haven't dwelled on this as much as we like to, so I won't claim that I know everything about it.
Okay, thank you.
Okay, I guess that's it. All right, thank you, everybody.